7th of December 1975, Greifswald Nuclear Power Plant, Lübmin, East Germany. Unit 1 runs at full power, 6 loops circulating coolant through a Soviet-designed Viva 440 reactor. At 11:08, a control room alarm announces a fault in the 6 kV standby switchgear, an electrical system formerly not required for reactor operation. An electrician's switching error produces a high short-circuit current. An automatic breaker fails to clear it. For 7.5 minutes, fault current heats 120 meters of cable until insulation ignites. Flames run through a shared cable tray between turbine and reactor buildings, destroying power and control circuits. Within the hour, all 6 main coolant pumps trip, feedwater is lost, and the plant drifts toward what one report later calls virtually a station blackout. International reviews will classify it as a safety-significant fire. But on this afternoon, operators face a simple question. With no designed cooling path intact, how do you keep a reactor core from overheating? The first Viva 440 pressurized water reactor in the German Democratic Republic entered commercial operation on 12th of July 1974. Unit 1 at Greifswald, on the Baltic coast near Lübmin, represented Soviet nuclear technology exported beyond its borders. 6 primary coolant loops, 2 220 megawatt electric turbine generators, and a confinement system instead of the full Western-style containment. Design documentation emphasized defense in depth. Multiple 6 kilovolt buses, emergency diesel generators, independent safety trains, redundant feedwater, and boron injection systems created layers of protection against equipment failure or operator error. The OECD Nuclear Energy Agency would later describe it simply: a safety-significant fire occurred in Unit 1 of the NPP Greifswald in the former Eastern Germany. That single sentence, buried in technical annexes, understates the event's impact on nuclear safety thinking. The VVER 440 Model 230 design featured 6 horizontal steam generators, each holding roughly 45 cubic meters of water inventory, steel pressure vessel, early generation instrumentation and control systems, limited fire protection by Western standards. The plant's electrical architecture relied on 6 kV backup distribution and switchgear, main and emergency feedwater pumps, high-capacity boron injection pumps designed for reactivity control rather than heat removal, and a pressurizer with safety valves as the last automatic pressure limiter. Soviet design organizations worked with the East German utility and regulator to implement what they believed was a robust system. Multiple trains of safety equipment, backed by separate diesel generators and independent power buses, should preserve cooling after any single failure. That premise, separation redundancy, defense in depth, formed the foundation of the plant's safety case. But separation exists in design documents and in physical reality. And at Greifswald, reality differed from design in one critical aspect: common cable ducts with limited barriers between redundant trains. A single fault in the 6 kV system could propagate along shared routes, affecting several safety-related systems simultaneously. The Nuclear Energy Agency's post-event analysis would note this vulnerability explicitly. The site layout told the story. Reactor building, intermediate building, turbine hall, cable trays running through connecting structures, carrying power and control circuits for pumps, valves, instrumentation, all the systems needed to maintain cooling after a reactor trip. In a plant designed for redundancy, these ducts represented a common pathway. One cable, routed through a shared tray, would soon test every layer of design logic at once. The morning of 7th of December 1975 began as routine. Unit 1 operated at power. The 6 kV standby distribution system, according to procedures, was not required for reactor operation. Maintenance work on the grounding switch between the standby transformer and its bus was considered low-risk electrical work, the kind performed regularly without special nuclear safety oversight. At 11:08, the control room log recorded a cable fire alarm in or near the 6 kV switchgear feeding standby power. What happened in the switchgear room would take years to fully reconstruct. An electrician performing work on the standby transformer made an error. Exact details remain sparse in open literature, but the effect was immediate and severe. a three-phase short circuit developed, and high short-circuit current began flowing through the 6 kV cable. Design expectations said the fault would clear rapidly. Protective devices, circuit breakers, fuses, relays existed precisely to interrupt fault currents before damage occurred. But a 220 kV circuit breaker, somewhere in the chain between the standby transformer and the distribution bus, failed to operate automatically. The fault persisted. For 7.5 minutes, high current heating stressed roughly 120 meters of 6 kV cable. Copper conductors, insulation, protective jacket, all heating beyond design limits. Eventually, someone manually tripped the defective 220 kV breaker, but by then thermal damage was done. The OECD Nuclear Energy Agency's reconstruction noted the sequence precisely. The fire was ignited by a short circuit on a 6 kV cable that lasted for about 7.5 minutes and overheated the cable over a distance of about 120 Nm. The lack of selective protection and fusing on the 6 kV side, a feature that might have isolated the fault more quickly, allowed the current to persist. Design reviews assumed breakers would function. This one did not. At this stage, the nuclear safety significance remained unclear. A 6 kV backup system, formerly not required at power, was on fire. Operators had not yet seen the consequences ripple through other systems. They did not yet know that this single cable fault, in a system considered non-essential, would remove almost every path to cooling the reactor core. The paradox was already forming. On paper, the 6 kV backup system was secondary, supplemental, non-critical. In practice, its failure through a common cable duct would prove to be nearly catastrophic. Heavy smoke filled the intermediate building that connected the turbine and reactor structures. The fire brigade responded, but visibility was poor and smoke removal systems were inadequate for the long turbine hall. The burning 6 kV cable did not simply fail and extinguish. Instead, the OECD review documented what happened next. The fire spread over the whole cable tray, also destroying other power and control cables. Cable insulation became fuel. Flames propagated along the tray, consuming not just the original 6 kV power cable, but also instrument cables, control circuits, and redundant safety train wiring that happened to share the same route. Design documents had treated these ducts as passive infrastructure. Conduits, not hazards. Physical separation existed in some areas, but the main cable route through the intermediate building combined multiple trains with minimal fire-resistant barriers. The turbine hall stretched roughly 1,000 meters in length, according to East German analyses. Most of this volume lacked automatic fire detection or fixed suppression systems. Manual firefighting became the only defense, and manual firefighting takes time. Smoke, heat, and constrained access limited the brigade's effectiveness despite adequate staffing. Later international fire risk studies would return to this configuration repeatedly. The OECD and IAEA used Greifswald as a teaching example. How cable ducts, when inadequately protected and segregated, can transform from benign infrastructure into single points of failure. How turbine hall fires, starting in equipment considered non-nuclear, can propagate into safety-significant systems through shared routing. As the fire spread, more circuits failed. Power to pumps, control signals to valves, instrumentation channels. The plant's redundancy, carefully designed into separate trains, collapsed because those trains shared a common physical pathway through the burning building. The cable tray fire lasted approximately 92 minutes before crews fully controlled it. By then, a large number of electrical cables were destroyed, phrasing used in later reports to summarize damage that was both extensive and precise. 5 of 6 main coolant pumps lost power. Main feedwater pumps went offline. Emergency feedwater systems became unavailable. Instrumentation channels degraded. Design documents had assumed that structural separation between turbine and reactor buildings, plus some degree of train separation, would prevent this. They had not assumed a shared intermediate building with a main cable route carrying multiple critical systems together. That assumption was now invalidated by fire and smoke. The reactor scrammed. Turbine tripped. Main coolant pumps lost power and coasted down. All within minutes of the cable fire alarm, the control room filled with alarms, not the pattern of a single equipment failure, but the cascade signature of a common cause event affecting multiple systems simultaneously. Expected response: even after a reactor scram, main or emergency feedwater should remain available from multiple trains, backed by separate 6 kV buses and emergency diesel generators. Actual situation: destroyed cables meant all main and emergency feedwater pumps were unavailable. The plant was approaching a station blackout, loss of off-site power combined with loss of on-site emergency power, and simultaneously a loss of heat sink scenario. Yet the reactor vessel remained intact. The primary circuit held pressure. The core itself was undamaged. This was not a loss of coolant accident in the traditional sense. It was something more complex, a functioning reactor system deprived of its designed heat removal mechanisms. Operators watched indications degrade as instrument cables failed. Some channels remained reliable, others displayed erratic readings or went dead entirely. Later, risk assessment analysts would describe Greifswald as one of 2 major blackout incidents used to evaluate the robustness and limits of VVR 440 safety systems. Decay heat became the enemy. A recently scrammed, pressurized water reactor core still emits roughly 6 to 7% of its previous thermal power immediately after shutdown, decaying exponentially over hours and days. For a VVR 440 at full power, roughly 1,375 megawatts thermal, that meant tens of megawatts of residual heat, equivalent to several industrial boilers, demanding continuous removal. Main coolant pumps were gone, no forced circulation. The primary system shifted to natural circulation, hot coolant rising from the core to the steam generators, transferring heat across tube walls, cooler water descending back to the vessel. A passive, reliable mode, but only if the secondary side of the steam generators could absorb and reject that heat. Each horizontal steam generator initially contained about 45 cubic meters of water inventory. That inventory could absorb heat through boiling, with steam released to the condenser or vented to atmosphere. This process bought time, several hours of margin, but it was finite. As steam generators boiled dry, heat removal would stop. Primary temperature and pressure would rise. Eventually, the pressurizer safety valves would lift to prevent overpressure. Some primary circuit instrumentation, pressurizer level, certain temperature readings, became unreliable or unavailable as cables burned. Operators had to infer core conditions from secondary side behavior and the few surviving channels, pressure trends, temperature estimates, indirect signs. Fire event summaries would later classify Greifswald as involving loss of all core cooling for some period and multiple safety systems impacted. That clinical phrasing represented a desperate reality. In the control room, with no normal path to remove decay heat, the clock was running. Attempts to start the emergency diesel generators revealed the full extent of cable damage. 3 EDGs provided backup power for Unit 1. Design basis: at least 2 should survive any single fire or equipment fault, preserving redundant injection and feedwater capability. Reality: control and auxiliary cables for 2 of the 3 diesels were destroyed in the common duct. Only 1 EDG could be started and loaded. The Nuclear Energy Agency reconstruction noted this as a critical limiting factor. Reduced emergency power capacity constrained operators' options for restoring cooling systems. Attention turned to the boron injection system. In a VVR 4040, high-capacity boron pumps inject borated water into the primary circuit to rapidly increase neutron-absorbing boron concentration, a reactivity control measure for shutdown or transient management. These pumps were designed for short-term use, not as a primary heat removal path, but they were available, powered by the 1 surviving diesel, and capable of injecting into the primary circuit at the prevailing system pressure. Technical analyses would later describe this as an extraordinary method of primary refilling and heat removal. Extraordinary because it fell outside normal emergency operating procedures, because boron pumps were never intended for this role, and because success depended on operator judgment about flow paths, pressures, and injection timing. After several hours of natural circulation and steam relief, with secondary water inventories depleting, operators made the decision. 1 boron pump was started. Cold borated water entered the primary system. Makeup flow maintained inventory. The core remained covered and cooled, even as steam generators continued boiling off their remaining water. Heat rejection still occurred through the secondary side, boiling in the steam generators, steam venting to atmosphere, decay heat carried away in that vapor. The boron pump provided the complementary function, maintaining primary inventory against shrinkage and minor leaks, preventing core uncovery. It was fragile. One diesel, one pump. No designed backup if either failed. No procedural guidance for how long this configuration could be sustained, or what would happen if the diesel ran out of fuel or the pump failed mechanically. But it worked. For several hours, this improvised cooling arrangement kept the core safe. The US Nuclear Regulatory Commission and NEA reviews would later highlight Greifswald as a teaching case, how equipment used outside its design basis can provide accident management capability, and how operator ingenuity can bridge gaps when design systems fail. The extraordinary method bought time to assess damage, time to search for alternative power sources, time to plan the next steps towards stable shutdown cooling. The immediate crisis, loss of all designed cooling paths, was contained, but the plant remained far from a controlled state. Late afternoon stretched into evening. The boron pump cooling method held, but everyone understood it could not be the final answer. The plant needed to restore secondary side feedwater, return to a more robust cooling configuration, and eventually transition to cold shutdown with residual heat removal systems properly aligned. The solution came from an unexpected source, Unit 2, still under construction. A Soviet erection team was on site, installing equipment for the second Viva 4040 unit. They had cables, they had knowledge of the plant's electrical systems, and they had equipment that Unit 1 desperately needed. US NRC fire incident analyses documented what happened. Secondary cooling was restored by routing a spare power cable from an alternate source, apparently from Unit 2, directly to one auxiliary feedwater pump. This cross-connection was not part of original emergency operating procedures. Design analyses had treated each VVER 440 unit as largely self-contained for safety purposes, minimizing inter-unit dependencies. But the fire scenario had invalidated those assumptions. Unit 1's internal emergency power was insufficient. Its cable routing had betrayed redundancy. An external power source became the lifeline. The temporary cable provided 6 kV or lower voltage feed to energize one auxiliary feedwater pump in Unit 1. Once that pump started, cold water flowed to the steam generators. Secondary side levels began recovering. The steam generators resumed their designed function as heat exchangers, removing decay heat from the primary side through normal thermodynamic processes rather than through emergency boiling and venting. Operators could now transition away from extraordinary boron pump makeup towards stable shutdown cooling. Primary pressure stabilized, temperatures decreased. The immediate threat of core damage receded further. Later fire probabilistic risk assessments would struggle with this event. How do you model inter-unit dependencies that aren't supposed to exist? How do you credit cross-connections that violate single-unit design assumptions? Greifswald forced analysts to confront those questions. The Nuclear Energy Agency and US NRC reviews confirmed the outcome. The core did not sustain any damage, and releases remained below prescribed limits. No radiological consequences, no fuel damage, no containment challenge. From a public safety perspective, the event ended successfully. But a question lingered, one that would drive safety evaluations for years. If Unit 2 had not been available, if construction had been delayed, if the Soviet team had been elsewhere, if cross-connection proved impossible, would the combination of boron pumps and steam venting alone have sufficed over many hours? How close had Unit 1 actually come to core damage? Throughout the event, operators worked with incomplete information. The cable fires had cut not just power but also signals. Instrumentation channels that should have provided direct readings of core parameters were degraded, unreliable, or completely failed. Expected situation: after any single fire, at least one full train of instrumentation and control remains available, allowing operators to monitor core parameters directly and make informed decisions about safety system actuation. Actual situation. Cable damage affected both power and I&C simultaneously. Operators had to infer core status using secondary side parameters and indirect signs. Steam generator pressure trends, relief valve behavior, the few surviving temperature and level indications, and engineering calculations based on known decay heat curves versus time since Scram. Pressurizer level, a key indicator of primary inventory, was among the casualties. Some temperature and pressure transmitters failed or showed inconsistent values. Parts of the reactor protection system and engineered safety feature actuation logic were compromised by smoke, heat, or direct cable failure. This forced operators into a decision-making mode more complex than any training scenario had prepared them for. They relied on what they could observe. Steam generator levels were still indicated, absence of high radiation alarms that would signal fuel damage, lack of containment pressure anomalies, and basic thermal hydraulic reasoning about how a recently scrammed reactor should behave. The OECD and IAEA fire risk reports would later cite Greifswald in discussions of combined loss of instrumentation and control due to cable fires. The event demonstrated that fire does not just disable equipment, it disables operators' ability to see and understand what is happening, complicating response even when some systems remain physically functional. Human factors became central. With limited data, operators accepted non-standard measures, using boron pumps for cooling, accepting a cross-connection from another unit, operating for hours without full indication of primary system conditions. These decisions required confidence, engineering judgment, and a willingness to step outside procedural boundaries when procedures no longer matched reality. Later fire probabilistic safety assessments would explicitly model loss of indication as a separate contributor to core damage probability, in part because of lessons from Greifswald. The event showed that instrumentation vulnerability deserves the same analytical rigor as equipment vulnerability. By the time stable cooling was restored and the plant reached cold shutdown, operators had successfully managed a multi-hour emergency with degraded indications, improvised equipment configurations, and no radiological release. It was a testament to training, discipline, and adaptability. It was also a warning. The plant's physical design had not adequately protected the information systems operators needed to respond to the physical challenge. While operators in the control room fought to maintain core cooling, the fire brigade fought to control the flames. The contrast between expectations and reality extended to fire protection itself. Design expectations, manual firefighting, supported by limited fixed water systems, is sufficient because fires are assumed to be localized and quickly detected. Plant fire brigades have adequate personnel and equipment for the fire loads present in nuclear facilities. Reality at Greifswald, the long turbine building, limited detection capabilities, absence of automatic suppression in most areas, and constrained smoke removal systems allowed fire and smoke to spread far along cable routes before crews achieved full control. The fire burned for approximately 92 minutes, not because the brigade was incompetent, but because the building's geometry and fire protection design constrained their effectiveness. The OECD Fire Database and IAEA experience reports would later use Greifswald as an example of how long-duration fires correlate with more severe cable damage. Fire duration matters. The longer flames and heat persist, the more cables fail, the more systems are affected, the greater the challenge to plant safety. Firewater systems required manual actuation. Segmentation of the turbine hall and cable tunnels was limited. Robust fire barriers between some compartments were absent or inadequate. The design had not anticipated this scenario, a self-sustaining fire in cable insulation propagating along trays with manual firefighters as the only barrier. Yet the firefighters succeeded in one critical respect. They contained the fire to electrical systems and cable areas. There was no direct impact on the reactor vessel, primary piping, steam generators, or confinement structures. The nuclear island remained physically intact. The fire's damage was electromagnetic, power and control, rather than mechanical. Event summaries classified Greifswald Unit 1 as a large switchgear and cable fire, with significant impact on safety functions. That classification understated the tactical complexity. A brigade working in smoke and heat, navigating a turbine hall over 1,000 meters long, protecting critical infrastructure while electrical systems shorted and sparked around them. When the last flames were extinguished and smoke finally cleared, the physical count of damage began. Widespread cable destruction, 5 of 6 main coolant pump circuits affected, emergency feedwater unavailable, instrumentation degraded. But the core survived, no radiological release occurred, and containment remained intact. The core survived, but only after a sequence of improvisations in a plant whose physical layout and fire protection had proven inadequate to its own safety assumptions. That gap between design confidence and operational reality would drive changes far beyond Greifswald itself. The Greifswald fire of 7th of December 1975 was not immediately shared beyond the German Democratic Republic. For more than a decade, details remained internal to the East German nuclear program and Soviet design authorities. But nuclear events have a way of surfacing, especially when their lessons matter to safety worldwide. In 1989, East German authorities released information about the 1975 fire as part of broader transparency initiatives. That year, Nuclear Engineering International published articles titled "German DR Releases Details of 1975 Greifswald Fire" and "Lessons from Greifswald Incidents." The technical nuclear community suddenly had access to a detailed case study of a cable fire that had disabled multiple safety trains, caused a near-station blackout, and required extraordinary operator actions to prevent core damage. Western analysts at Sandia National Laboratories, the US Nuclear Regulatory Commission, and the OECD Nuclear Energy Agency began reconstructing the event. They compared it to typical fire probabilistic risk assessment assumptions: cable fire propagation rates, damage thresholds, common cause failure modes, the effectiveness of manual suppression. Greifswald challenged assumptions. Fire PSA models had often treated cable fires as localized events affecting individual cabinets or small sections of tray. Greifswald showed that a single ignition source could propagate along cable ducts, affecting multiple trains over long distances and extended time periods. It demonstrated that scenarios involving loss of all core cooling for some period were not merely theoretical worst cases, but documented realities. The OECD Nuclear Energy Agency's Fire Risk State-of-the-Art report listed Greifswald among a small number of safety-significant international cable fires. The US NRC's NURIG CR6738, analyzing risk insights from fire incidents, included Greifswald in its selected cable fire compilation. IAEA experience summaries cited the event when discussing internal hazards and defense in depth. From an obscure incident in a closed East German facility, Greifswald became a reference case, a benchmark for validating fire PRA models, a teaching example for cable duct vulnerability, and evidence that common cause fire could disable engineered heat removal systems across multiple emergency power trains. The reconstruction process revealed details: the 7.5-minute fault duration, the 120-meter extent of overheated cable, the 92-minute fire duration, the loss of 5 of 6 main coolant pumps, the multi-hour period of improvised cooling, the use of boron pumps outside design basis, the cross-unit power connection. Each detail refined international understanding of fire risk. Greifswald shifted thinking from local cabinet fire scenarios toward plant-level common cause event in probabilistic models. It showed that cable routing, a detail often treated as a construction and installation issue rather than a safety-significant design choice, could determine whether a plant survived an internal fire without core damage. Soviet-designed plants had a reputation for strong adherence to detailed operating instructions. Procedures were comprehensive, prescriptive, and expected to be followed. Accident management concepts as understood in Western practice, flexible, symptom-based approaches that gave operators latitude for creative responses, had not yet fully developed in VVR operating culture of the mid-1970s. Yet survival of the Greifswald core depended on actions that fell outside procedures. The use of boron injection pumps as a makeup and cooling source was not a procedurally guided response. Cross-connecting power from Unit 2 to Unit 1 had no written instruction. These were on-the-spot engineering judgments, using equipment outside its design basis, connecting systems never intended to be linked. Eastern European and IAEA technical papers on VVER accident management later cited Greifswald, alongside the 1982 Armenia Unit 1 fire and station blackout, as formative events that revealed gaps between deterministic design basis thinking and real operational needs under severe stress. If human improvisation proved essential to preventing core damage, then procedures and training had to change to recognize that reality. The intended role of the boron injection system was reactivity control, injecting high-concentration borated water to increase neutron absorption in the core, suppressing power and maintaining subcriticality. Using it as a primary make-up pump to maintain inventory and indirectly support cooling represented a functional repurposing, creative, effective, but not in any emergency operating procedure. Similarly, the cross-unit electrical tie fell into a procedural void. No formal guidance existed for establishing such connections under emergency conditions. The decision required trust in the Soviet construction team's knowledge, confidence in the temporary cable's adequacy, and acceptance of a configuration that defied single-unit independence assumptions. Fire incident reviews explicitly classified some of Greifswald's recovery actions as credited human recovery actions, an acknowledgement that operators' non-procedural decisions contributed meaningfully to the safe outcome. But crediting human recovery actions in probabilistic assessments is complex. How reliable is improvisation? How much can safety analyses depend on creativity under stress? These questions drove the development of accident management guidelines and symptom-based emergency operating procedures in VVER fleets during the 1980s and 1990s. Greifswald became a case study. What had operators done? Why had it worked? How could future procedures capture that flexibility while still providing structure and guidance? The event showed that rigorous adherence to written instructions is valuable until the scenario transcends what instructions anticipated. Then, engineering knowledge, system understanding, and willingness to act outside boundaries become survival tools. The challenge for procedural development was preserving that adaptive capacity while reducing reliance on improvisation through better planning, more flexible guidance, and broader scenario coverage. If human improvisation is essential to safety, then training, procedures, and safety culture must evolve to support it, rather than constrain it. Greifswald was not the only troubling event in early VVER 440 history. On 9 October 1982, a similar fire-induced station blackout occurred at Armenia Unit 1, another VVER 440 V230. That event, combined with Greifswald's eventual disclosure, prompted systematic reviews of the entire first-generation VVER 440-230 fleet. IAEA safety assessments identified generic weaknesses, limited containment capability, confinement leakage potential, emergency core cooling system design constraints, and vulnerability to internal hazards including fires. Cable routing emerged as a recurring issue. First-generation VVER 440s often lacked robust separation between redundant safety trains, allowing common cause failures from fire, flooding, or other internal events. WENRA, the Western European Nuclear Regulators Association, examined nuclear safety in candidate countries seeking European Union membership. Their 2000 paper cited two major blackout incidents, the Greifswald 1 fire in 1975 and Armenia 1 fire in 1982, as evidence that VVER 440-230 designs possessed both surprising robustness, the cause survived, and troubling vulnerabilities. Survival required extraordinary operator actions and fortuitous circumstances. The contrast was stark. On one hand, VVER 440 thermal hydraulic design, large coolant inventory, 6-loop configuration, passive natural circulation, proved resilient. On the other hand, electrical architecture, cable routing, fire protection, and instrumentation design showed deficiencies in redundancy and diversity. German reunification after 1990 brought Greifswald's 5 units under Western regulatory scrutiny. The GRS, Gesellschaft für Anlagen- und Reaktorsicherheit, conducted comprehensive safety evaluations, referencing significant occurrences including the 1975 fire, and a later 1989 SCRAM system failure. While these assessments were site-specific, they fed into broader discussions of VVER 440-230 generic issues. International assistance programs, EU FAIR, TARKIS, bilateral agreements prioritized safety upgrades for Soviet-designed reactors in Central and Eastern Europe. Greifswald's experience informed backfitting requirements, improved fire barriers and detection in cable ducts, rerouting of cables to enhance train separation, additional or reconfigured emergency feedwater systems, upgraded emergency power with better physical protection and control cable segregation. For some plants, these upgrades proved economically feasible. For others, including all VVER 440 V230 units, the scale of required modifications was deemed cost-prohibitive given the plant's age and remaining operational life. The European Union's Agenda 2000 framework classified first-generation VVER 440-230 reactors, along with RBMK 1500 units, as not economically upgradable to internationally acceptable safety standards. One non-radiological fire, one 7.5-minute electrical fault, one cable duct in a turbine building. These influence safety programs, regulatory classifications, and ultimately closure decisions for more than a dozen reactor units across Eastern Europe. The fire at Greifswald on 7 December 1975 cast a long shadow. The post-Cold War period brought fundamental reassessments of Soviet-designed reactor safety. Western and Eastern regulators, previously separated by geopolitical boundaries, began sharing data and methodologies. Greifswald and Armenia's fire-induced blackouts moved from classified national incidents to international reference cases. EU programs, FAIR for candidate countries, TARKIS for the former Soviet Union, funded safety evaluations and upgrade projects. Regulatory directives required improved separation of safety trains, addition or enhancement of fire detection in turbine halls and cable spaces, upgrading of emergency power supplies, and relocation or fireproofing of vulnerable cables. The World Nuclear Association and IAEA documented outcomes. Many first-generation VVER 440-230 units were shut down permanently. Greifswald's 5 units closed following German reunification. Bulgaria's units 1 to 4 at Kozloduy closed as a condition of EU accession. Some upgraded VVER 440 units, later Model 213 variants, and certain modernized sites in Russia and Armenia continued operation under enhanced oversight and with substantial backfits. Specific upgrades driven partly by Greifswald's experience included new or reinforced cable separation and fire barriers in tunnels, modern detection and fixed suppression systems installed in turbine buildings and cable spaces, additional or reconfigured emergency diesel generators with diversified auxiliary power paths, and enhanced accident management procedures explicitly addressing loss of all feedwater and station blackout scenarios. These changes were not merely procedural. They required physical modifications, rerouting hundreds of cable runs, installing fire-resistant barriers, adding suppression systems, building new switchgear rooms or diesel generator bunkers. The cost was substantial. For older plants with limited remaining operational life, the economics favoured closure over upgrade. EU and IAEA assessments repeatedly cited the blackout incidents at Greifswald and Armenia as empirical justification for these programs. The events were evidence, not theoretical concerns, but documented realities, demonstrating that cable fires could disable multiple safety trains, that station blackout in VVER 440 designs was a credible scenario, and that survival might depend on factors: construction crews on site, adjacent unit availability, operator creativity, too uncertain to be formalized in safety analyses. Despite the absence of radiological release, Greifswald was retrospectively classified at approximately INS Level 3, a serious incident, based on its safety significance. The International Nuclear Event Scale considers not just consequences, but also degradation of defense in depth. A multi-hour loss of designed cooling paths, partial station blackout, and reliance on improvised measures met that threshold. A 6 kV cable fault, a failed breaker, 7.5 minutes. These small initiators had large consequences, not in radiation dose, but in reshaping how an entire class of reactors was understood, regulated, and ultimately retired. The OECD Nuclear Energy Agency's simple sentence endures: a safety-significant fire occurred in Unit 1 of the NPP Greifswald in the former Eastern Germany. That phrasing, deliberate in its understatement, has appeared in technical annexes, fire risk reports and safety conference presentations for decades. The numbers remain stark. A 6 kV short circuit lasting 7.5 minutes over roughly 120 metres of cable. Fire duration approximately 92 minutes. Loss of 5 of 6 main coolant pumps. Loss of all main and emergency feedwater systems. Temporary loss of all designed core cooling paths. Use of a single boron injection pump powered by one surviving emergency diesel for sustained makeup. Cross-connection from an adjacent unit under construction to restore auxiliary feedwater. No core damage, no radiological release, no documented worker exposures beyond regulatory limits. Radiologically, Greifswald was a non-event. From a safety analysis perspective, it was transformative. Fire probabilistic risk assessments now explicitly model cable duct fires as potential common cause initiators. Separation of redundant trains is not just a design preference, but a quantified risk factor. Loss of indication due to fire receives analytical attention comparable to loss of equipment function. Operator recovery actions, particularly those outside written procedures, are recognized as both essential and uncertain, requiring careful treatment in risk models. More than a dozen VIVAR 440-230 units were affected by upgrade or closure decisions, influenced partly by lessons from Greifswald. Safety programs in Eastern Europe and the former Soviet Union incorporated fire protection standards informed by the event. International guidance documents, IAEA, OECD, NEA, WENRA, cite Greifswald when discussing cable fires, station blackout, or loss of heat sink in pressurized water reactors. Greifswald demonstrated vulnerability and resilience in the same breath. Vulnerability: a single electrical fault in a non-safety system propagated through common cable ducts, disabling designed cooling paths and challenging core safety. Resilience: large coolant inventory, passive natural circulation, operator adaptability, and fortuitous availability of alternative power sources allowed survival without fuel damage. That duality captures the complexity of nuclear safety, systems that are simultaneously robust and fragile, depending on which failure modes are tested. Greifswald tested a mode, common cause fire, affecting multiple trains and instrumentation that design analyses had underweighted. 7 December 1975 became one of the few dates where a non-radiological fire forced a worldwide recalibration of cable fire risk, not because the core failed, but because documented system behavior diverged sharply from design expectations. The gap between confident prediction and measured reality, between defense in depth on paper and defense in depth under fire, shaped nuclear safety thinking for a generation. In the history of nuclear incidents, Greifswald occupies a particular space, an event without radiological consequence that nonetheless influenced safety programs globally. The signature is not measured in sieverts, but in redesigned cable trays, upgraded fire protection systems, enhanced procedures, and a deeper understanding of common cause vulnerability. The 6 VVR 440 loops at Greifswald ran for years after 1975, until German reunification brought permanent shutdown. The site is now under decommissioning, fuel removed, structures being dismantled. But the lessons, documented in OECD reports, IAEA safety guides, probabilistic risk assessments, regulatory standards, continue to inform how nuclear facilities worldwide protect against internal fires. A warning placard, perhaps metaphorical, could summarize it. 7.5 minutes can reshape an industry. One cable duct can challenge a fleet.